Hey, ladies and gents, hope you guys are doing well and enjoying the day. So, today we're going to be going over this case study looking at inhibition of enzymes. It's called Magic Bullets. And it seems a little violent, but it's about enzymes in health. All right, so just a routine checkup. Oliver Casey, age 53, was visiting his doctor, Ariana Kagan, for his annual physical. Aside from feeling a little more tired than usual, which he attributed to an increased responsibilities at work, Oliver thought he was in good health. However, during the physical examination, Dr. Kagan noted that Oliver had an enlarged spleen. I'm going to order some blood work to see if we can figure out why your spleen is enlarged. You may have an infection. It's probably nothing serious, Dr. Kagan told Oliver. Oliver left the doctor's office that day feeling a little unsettled, but hopeful that his enlarged spleen was caused by nothing more than a virus. Okay, looking at the results. Oliver's palms are sweaty, knees weak, arms are heavy, and his heart was racing as he sat across from Dr. Kagan in her office. He knew it couldn't be good news if he had been called in to discuss with blood test results in person. So here are the findings. So his white blood cell count, 225 times 10 to the ninth. That's pretty high. It says normal range 4.5 to 10 times 10 to the ninth. So if we look at the blood smear, purple, white blood cells stain purple. So in the healthy blood, you see just a few white blood cells and lots of red blood cells. But in Oliver's blood smear, holy smokes, there's a lot of white blood cells going on. So when our first clicker question, it said based upon the data shown in the previous slide, Oliver appears to be suffering from what? Looks like a good answer there is B, leukocytosis, because he's got way too many white blood cells. Leuko means white, cyto is cell, osis is condition of. So if you got too many white blood cells, that's leukocytosis, the type of cancer. So Oliver sat in stunned silence while Dr. Kagan reviewed his blood test results. Your very high white blood cell count and enlarged spleen prompted me to perform some additional testing on your blood cells, and I'm afraid the results are not very good. The results reveal that your blood cells contain a mutation that has caused you to develop a blood disease called chronic myeloid leukemia, or CML. This is a slowly progressing cancer of the blood cells. I'm going to refer you to a doctor called a hematologist who specializes in blood diseases who will discuss your treatment options. Chronic what? Replied Oliver, snapping out of his silent state. Dr. King explained to Oliver a little more about what CML is and what causes the disease. So here we see CML. It's an overproduction of a type of white blood cell called a granulocyte. So these are the white blood cells that go out and do a lot of attacking of pathogens in the body. So here it says, this is sort of interesting. The vast majority of cases of CML are caused by a chromosomal translocation. We haven't really gotten into this yet, but what happens is normally in meiosis, you have crossing over occur and homologous chromosomes, the chromosomes that are similar in size, shape, banding pattern, like one from mom, one from dad, they'll swap bits of their ends. But here, non-homologous chromosomes, in this case, chromosomes 9 and 22, swap bits and pieces, which have different types of genes on them. Okay, homologous chromosomes usually have the same types of genes on them, but if you have different chromosomes, they have different types of genes on them. So with this translocation chromosome, you wind up with this tiny little Philadelphia chromosome, must be named after cream cheese or steak sandwiches. But these little chromosomes have a newly created protein on them. So that's sort of fascinating because here you have this ABL gene and then this BCR gene. But when this translocation occurs, you can combine them and you make this sort of new protein. All right, so BCR-ABL is a mutated version of the ABL protein, which is a tyrosine kinase. Ooh, kinases, we've talked about those, right? They activate cells, they make things happen. So what happens, or more specifically, is that a kinase is an enzyme that catalyzes phosphorylation. So what that means is kinases, what they do is they ensure that some molecule, generally speaking called a substrate, gets phosphorylated. So kinases can sort of strip a phosphate off of ATP and then hand it to some other molecule. And when you hand that phosphate to another molecule, what's it going to do to it? Change its shape and activate it. Okay. So tyrosine kinases are sort of interesting because what they do is they just sort of pass things off. they strip a phosphate off of ATP, and then they hand that phosphate to another molecule. And when they do that, that molecule changes its shape and becomes active. So mutating a tyrosine kinase can lead to overactivity or underactivity of phosphorylation. Let's see. Question number 2. What part of an enzyme binds to the substrate? Ooh, it's the active site. D is our winner for that one. 3. Which of the following statements is false? A, the shape of the active site is determined by the amino acid sequence. And that's true. B, the shape of the active site is constantly changing, allowing the enzyme to bind to many different substrates. Woo, woo, woo. Red flag there, right? So the active site can interact with and sort of bond weakly with the substrate, but it's not going to be changing its shape all the time. So B's our false statement there. Question 4. One function of the Abl kinase is to phosphorylate substrates that tell white blood cells to grow and divide. The Abl kinase is mutated in CML, giving rise to BCR-ABL protein. Based on the normal function of Abl in white blood cells, how do you think the mutated version of the kinase, the BCR-ABL, contributes to the development of CML, a cancer of white blood cells? Well, if you think back to the blood smear for Oliver, he's got a lot of white blood cells there, right? So if this Abl protein normally phosphorylates pathways telling white blood cells to grow and divide, and it's mutated and it's overactive, it's going to be A. The kinase becomes overactive, you get too much enzyme activity, and you're cranking out all these white blood cells. All right, so under normal circumstances, typical circumstances, this kinase, this enzyme is regulated. You can switch it on, switch it off, and you only really make these white blood cells when needed. BCR-ABL, this is a mutation that causes it to be constitutively active. What that means is its shape has changed so that it's always switched on. And if it's always switched on, it's going to continue these signals telling cells to divide. All right, so we're visiting the specialist. Oliver is meeting with the hematologist, Dr. Clement. Well, the doctor was optimistic about Oliver's treatment options, particularly since they had caught the cancer at a relatively early stage. We will start you on a drug called imatinib, which more commonly known as Gleevec, and we will monitor your white blood cell count to see how you respond to the drug, Dr. Clement advised Oliver. Please see the receptionist to schedule a follow-up appointment and make payment, and call the office if you experience any negative side effects. Oliver left the office and picked up his prescription for Gleevec. Isn't it amazing that you can have a cancer and then they'll just prescribe a medication, you take your medication to stop the cancer. All right. Predict the mechanism of action of imatinib. Which of the following mechanisms would best treat Oliver's cancer? So what do you want this drug to do? Well, if the kinase is switched on, you don't want that to be signaling all the time. So if we look at A, imatinib inhibits the function of all kinase enzymes. You don't want that because you'd shut down all sorts of pathways in the body. If we look at B and D, we don't want to promote the activity of kinase. The best answer there is C. Imatinib inhibits the function of the BCR-ABL kinase, so it goes after that particular enzyme. All right, so you could have watched that animation. So in the animation, it's really nice. They've got the ABL kinase, and then with the BCR-ABL mutation that can get switched on, and then ATP docks there, it can strip off the ATP and hand it off to enzymes or substrates that activate these pathways to make white blood cells. So the question is, what type of inhibitor is Gleevec? If you watch the animation, you see that it's a competitive inhibitor. The medication sort of docks in that ATP pocket so that ATP can't fit in there, so you can't transfer the phosphate group on over to the substrate. So it basically blocks that particular enzyme, and so you don't overproduce those white blood cells. So here, again, it's the answer. Gleevec is a competitive inhibitor. So again, it competes for access to that active site or that pocket for ATP, and then the phosphate can't get stripped off and handed over to the substrate. Blood tests, and more blood tests. Oliver had to admit it. He was getting used to the needle stick. 18 months ago, Dr. Clement had warned Oliver that it would be crucial to routinely monitor Oliver's blood to determine if the Gleevec was effectively fighting his cancer. And Dr. Clement was right. There sure were a lot of blood tests. And each time Oliver went to the phlebotomy lab, he hoped that his test results would reveal good news. All right, so here it says refer to the graph, charting some of Oliver's blood tests over the past 18 months. Based on this graph, how's the treatment looking? Well, if we look over time, what's happened to his white blood cell count? It's dropped and dropped and dropped. And if we recall, the normal range was like 4 to 10 times 10 to the ninth. And if we look, here's 50, 40, 30, looks like we're down in single digits. So seems to be doing the job. Predict what would happen if to Oliver's white blood cell count if he stopped taking Gleevec. Well, shoot, if he stopped taking that, the mutation's still there, right? So you've got this active enzyme, and the BCR-ABL enzyme would keep cranking out phosphorylated substrates, and he'd make too many white blood cells. His cancer would come back, right? Or well, I guess he's always got the cancer, but the increase in white blood cells would occur. So the best answer there is C. His white blood cell count would rapidly increase above the normal and healthy range. Feeling good. Oliver was pleased. It had been about 18 months since his initial diagnosis of CML, and it appeared that Gleevec was working. His white blood cell counts were back within the normal range, and Dr. Clement indicated that other testing revealed that the BCR-ABL mutation was no longer detectable in his blood cells. He would continue to have his blood tested every 3 months and was scheduled for a checkup with Dr. Clement in 6 months. Provided everything continued to look good. So, again, just take the medication that blocks that active site, and that quiets the signaling pathway. All right, here we have some troubling results. Dr. Benjamin Clement frowned as he looked at the latest blood tests of his patient, Oliver Casey. Oliver had been taking imatinib for a little over 21 months now and had responded beautifully, but the most recent blood work showed Oliver's white blood cell count was very high again. And genetic analysis revealed the presence of BCR-ABL mutant kinase in his cells again. It's time to call in Oliver for a discussion. All right, in groups of 2 to 3, discuss what would be the possible causes of Oliver's relapse. What do you think could be causing the relapse? I don't know. That mutation was handled pretty well with Gleevec. Could he have experienced another mutation that altered the shape of the enzyme again? I don't know. Let's look and see. Resistance. Dr. Clement shared the bad news with his patient. I'm sorry, Oliver, but it appears that the Gleevec you've been taking is no longer working against your cancer, and your white blood cells are growing out of control again. We'll do some genetic testing to confirm, but the most likely cause of this relapse is that the BCR-ABL gene has mutated once again, and that mutation has rendered the protein resistant to the Gleevec that you've been taking. So, again, you have this mutation, and it can cause overactivity of the enzyme. You can use Gleevec to block that, but what if you have an additional mutation to the DNA that causes the shape of the protein to change yet again? Then the drug might not work. So this is a pretty short clip. Let's watch this one.
BCR-ABL is a machine. It's moving back and forth between this inactive and active shape. What these mutations do is force the protein into the active conformation. If you also remember, I made the point that when Gleevec binds, it very cleverly locks the BCR-ABL protein in the inactive conformation. So if you have a mutation now that's making the protein stay in the active form all the time, Gleevec's not going to be able to bind.
Okay, so you had this little loop here from the previous video. There's the loop is in an inactive spot, and then the loop is in an active spot, so it makes it easy to hand off that phosphate group to the substrate. Gleevec would fit in here when the enzyme is switched off in the inactive form. But here they're saying, well, what if you have another mutation and change the shape of this loop? So now the loop is always switched on. If the loop is always switched on, then Gleevec isn't going to fit into that pocket anymore, and now the enzyme is constantly active.
So what I'm showing you on the left is the inactive conformation. On the right is the mutant form, which creates this active conformation. Now, in both forms, ATP, the yellow molecule, can bind, no problem. But now when you try to fit Gleevec in, because of how nicely and tightly it fits into the inactive conformation, it can't fit into the mutant BCR-ABL.
Okay, so let's cancel that. So again, When you have that second mutation, the enzyme stays switched on, and then the Gleevec can't fit into that pocket anymore. So ATP is able to fit in there. The phosphate gets stripped off ATP and then handed off to the substrate. So we got some work to do with that. Let's see. According to the video, what do resistance mutations do to render imatinib or Gleevec ineffective? Let's see. Mutation. Resistance allows ATP to bind. If we look at C, the resistance allows ATP to bind to that pocket, but Gleevec doesn't fit in there anymore. So again, it looks like, in the animation anyway, it looks like the pocket was a little bigger. So Gleevec wouldn't be stable in that pocket. So it would move out and then ATP could fit in there. Dasatinib versus imatinib. Dr. Clement sat in his office reviewing the most recent genetic testing results with Oliver. As I expected, he said, you have acquired a resistance mutation in BCR-ABL that is preventing Gleevec from doing its job. But the good news is we have another drug, dasatinib, that should be able to counteract this mutation. I'm going to call in a prescription for dasatinib that you should start right away. Oliver was skeptical. If Gleevec wasn't working against his cancer, what was so magical about this new drug, dasatinib? Shape, right? Shape and function. All right, so let's look at this is, I think, a pretty quick animation looking at the difference between dasatinib and imatinib.
The drug that was sent to us, the one that worked the best, is a drug that now goes by the name dasatinib. Let's see how it works in the next video. If you could please roll that one. You can see dasatinib fits nicely in either pocket.
So it looks like it's got a larger
and in both
head
cases,
on that.
It prevents ATP from binding, so it accomplishes the mission.
Okay, so here with dasatinib, again, it looks like they've got the head of the molecule a little larger. So whether BCR-ABL is in its inactive shape or its active shape, dasatinib could fit in that pocket and block ATP from entering. Oh, okay. That was that. All right, no more biovisions. Okay, question 10, what type of inhibitor is dasatinib? Well, it's still fitting in that active site, right? So it's still a competitive inhibitor. Which of the following distinguishes the function of dasatinib from the function of imatinib? Dasatinib, looks like B is our winner there. Dasatinib, it binds to that pocket, whether the BCR-ABL protein is in its inactive or active shape, its conformation. Imatinib, it only worked when BCR-ABL was inactive. So again, if you have that second mutation and that loop opens up so that it's always active, imatinib doesn't work, but dasatinib does. A little bit of shape difference makes a difference, or shape makes a difference. Okay, the development of inhibitors block the function of BCR-ABL has revolutionized the treatment of this leukemia. Mortality has dropped from 10 to 20% to 1 to 2% per year. Isn't that amazing? By designing a molecule to fit inside of an enzyme, you can significantly reduce a person's odds of dying from this cancer. So now it's treated as a chronic disease rather than life-threatening cancer. Tyrosine kinase inhibitors are a lifelong treatment. So if you stop taking the drug, well then, the ATP is going to be handed off. You're going to activate these enzymes. You're going to overproduce these white blood cells. Resistance mutations are always a threat. New tyrosine kinase inhibitors that are effective against known resistance mutations are currently in clinical trials. So a mutation is a change in shape, right? So what type of mutation you have, do you know how it's going to change the shape? It's all contextual, right? It depends on the mutation. So if people experience these changes, you could change the shape of the enzyme in ways that don't allow current drugs to fit in that pocket and prevent ATP from being stripped of its phosphate group. Allogeneic bone marrow transplantation is the only true curative treatment, although it's not too common. There's some inherent risk to a bone marrow transplant. So if you've got a drug that works to block it, then that's a good step to take. All right, well, that's it. Thank you guys for sticking with this. Hope you have a great day. It's a cool example of what enzymes can do.